Hi everyone, this is Xinda Wang. This is Shu Wang. Today we are going to talk about our paper PatchDB on large-scale security patch dataset. This is a joint work with Dr. Peng Binfeng, Professor Kun Sun, and Professor Shil Zhaodia from George Mason University. Security patches are of great importance since they contain both vulnerable code and corresponding fixes. They can be used for detecting vulnerabilities and testing patch presence in downstream applications. However, existing open source patch datasets have several limitations. First, their size are too small to enable a robust model training. Second, they are collected from specific type of projects, which may lead to biased conclusions. Also, some salient security patches are mislabeled as non-security ones. So in our work, to enable patch or vulnerability-related research, we construct a new patch dataset called PatchDB, including 3 parts. The first one is a dataset constructed by crawling all the related hyperlink from National Vulnerability Database. Since some security patches are not included in the NAD, we further enlarge our dataset by finding more patches in the wild. To further increase the varieties, we generate an artificial dataset by using our syntactic algorithm. Then I will introduce each part one by one. Our first part is to extract the security patches from NAD. For each CVE entry, we download its corresponding security patches from the Git hyperlink labeled as patch. Here we focus on C and C++, and in this way we collect around 4,000 samples. However, not all security patches are included in the NAD. We found that on GitHub, around 8% commits are salient security patches without a CVE ID. They provide a source for augmenting our existing NAD-based patch dataset. So here, we perform an augmenting algorithm to help enlarge the dataset. Given security patches extracted from the NAD, we first find a set of candidates that are most promising samples to be security ones. And then we perform manually checking to see if it is a security or non-security patches. If so, we merge them into existing security dataset. If not, we just put it aside. Then we can continue this loop until we find enough security patch samples. In such process, the key problem is how we find the candidates. Finding the most promising samples can help greatly reduce our human efforts during the verification. That's why we propose our nearest link search algorithm. For each security patches already identified, we perform nearest link search to compute and locate its nearest neighbor in the feature space as candidates, so that we can shrink the search range to enable a more effective verification. To further increase the varieties, we generate an artificial patch dataset. Previous research has found that around 70% security patches make modification on sanity checks. So here, our synthesis strategy is to add variants on if statements in existing patches, since a patch is a set of code changes between 2 versions. So here we directly make modification on original or patched versions, and then we can compute the new difference as an artificial patch.
Our evaluation focuses on answering 5 questions, including the details and the performance of data augmentation algorithms, and the real properties and quality of PatchDB. To construct the wide-based dataset, we use 200,000 randomly selected commits from more than 300 popular C and C++ GitHub projects. After nearest link search, up to 30% of the candidates are secure patches at the verification. The radio will increase with the search range. Finally, the wide-based dataset contains 8,000 secure patches and 24,000 non-secure patches. We also evaluate the effectiveness of nearest link search with 3 traditional methods, including the brute force, directly searching from the wide, and pseudo labeling and uncertainty-based labeling. We find the efficiency of our method is more than twice or even triple of others because our method directly finds the similar patterns of existing security patches, and our method can save lots of label costs. If we apply synthetic data with NVD-based dataset and NVD plus wide-based dataset, respectively, the performance will be improved in both cases. However, in the second case, we only achieve 0.1% improvement in precision and recall. The experimental results show that our oversampling technique is effective in the security patch identification test if we only have a small dataset. When we have a larger dataset, the improvement from oversampling is not obvious. After the data augmentation, we find the distribution of wide-based dataset is different from that of NVD-based dataset. So in PatchDB, we will have more patch variants to extend our application. Finally, we adopt 2 classification models, random forest and the recurrent neural network, to security patch identification test with PatchDB. We compare the performance with different training datasets. We find the models trained with both NVD-based and wide-based datasets have better generalization ability. And the RM model can achieve 92% precision and over 60% recall, which verifies the quality of wide-based dataset. In conclusion, we construct the first large-scale patch dataset called PatchDB. With data clearance and oversampling, our dataset will contain NVD-based datasets, wide-based datasets, and synthetic-based datasets. This dataset can be used in vulnerability detection, automatical patch generation, and even binary applications after further compilation. Thank you for listening. We are glad to accept any questions, and you can contact us by the following email addresses.